Okay, now that we know how to use Laplace transform to solve certain linear second-order differential equations with constant coefficients, um, the goal now is to be able to solve such problems where you have a right-hand side function that instead of being zero or something nice like a simple exponential, is actually a piecewise defined function. So functions equal to different formulas on different parts of the domain in T. So I'm going to break this material, which is from section 7.3 in the book, down to two parts. Today I'm just going to talk about how you Laplace transform certain functions that are defined in a piecewise manner. And then in the other part, which will be recorded next week, I will talk about how we use solve differential equations involving such piecewise defined functions. That'll actually be the last material of a semester, and then I'll record a review for final. I will be making a practice final exam. I still need to do it, but I'll be doing it soon. The final will be due a little more than like during finals week, so a little more than uh, 3 weeks or so from now. Um, okay, so first I need to introduce the simplest piecewise defined function, which is called a sorry, sometimes this thing refuses to cooperate. Okay. The unit step function, also known as the Heaviside function, is defined as follows. Okay. So I'll use a fancy script U, which is similar to the appearance in the homework, with a subscript of C, which I'll explain momentarily. Okay. Right, so this function is defined in two pieces. That's equal to 0 for t less than the value c that's specified here, and it's equal to 1 for t greater than or equal to c. So its function is 0 up to a certain point, it then jumps up to 1 and stays there. It can also be expressed as, whoops, okay. And I believe this is how it's done in WebAssign. So just a u with no subscript, but instead of being a function of t, it's a function of t minus c, where u of t is equal to 0 for t less than 0, and then is equal to 1 for t greater than or equal to 0. So this is the simplest form of a Heaviside function. It jumps from 0 to 1 at t equals 0, but then if I shift this function, so having a t minus c, we have a shift of a graph c units to the right. So that causes the jump from 0 to 1 to happen at t equals c instead of 0. Okay. All right. Now, so what I need to show you here is how do we perform Laplace transforms of this function. Now, we actually generally will be having this step function multiplied by some other function as part of a piecewise definition of some function, like a function that's defined in 2 or 3 pieces, for instance. So we have a rule for that. Okay, so it's the Laplace transform of the unit step function of t minus c, times some other function f that's also a function of t minus c. And that is equal to e to the minus c, whatever c is, times s, times f of s, capital F of s, where capital F of s is equal to Laplace transform of f of t. Okay. All right. So the idea is, if we just have this step function that's just stepping from 0 to 1 at t equals 0, so that would just be plain old u of t, so c would be 0, then that would not affect the Laplace transform at all. That little f of t would just transform to big F of s. And that's because the Laplace transform is an integral from 0 to infinity. Whatever's happening for t less than 0 does not affect it anyway. But if we shift the graph of a function by c units to the right, and still have it 0 for t less than c. So in other words, this function f is effectively switched on at t equal to c. It's switched off before that, in other words, equaling 0. So it's switched on at t equals c. What it does to the Laplace transform, all it does is multiply it by this exponential, this e to the minus cs. Okay. All right. So what that would mean is, if we're just transforming this unit step function by itself, then we would have this step function times 1. The Laplace transform of that would be e to the minus cs times 1 over s, because the Laplace transform of 1 is equal to 1 over s. But it's really this general formula that we need here for all the different examples that we'll see involving piecewise defined functions. So, got interrupted there, but let's keep going. So I'm going to walk you through some examples of how we use this to handle some piecewise defined functions. So this function f of t will be defined in 3 pieces. All right, so we have so first, from t going from up until t equals 1, t equals 0. Then once t equals 1, the function changes to t squared, and that will be in force from t equals 1 up until 3, and then after t equals 3, it'll go back down to 0. So, in order to obtain the Laplace transform of little f of t, we need to rewrite it in terms of unit step functions. So just one formula instead of these 3 separate ones. Okay, so first of all, the function is non-zero until t equals 1. So to account for the jump from 0 to t squared, so a function that does that, goes from 0 to t squared, is I'll call it f1 of t, and that is equal to a unit step function. It's a function of t minus 1. So in other words, a jump will happen at whatever t value is being subtracted here. It's happening at 1 times t squared. So what that function does is it accounts for the first two pieces anyway. Okay. So it jumps to 0. So it starts from 0 at t less than 1, and then t squared, t greater than or equal to 1. So it does most of what we need. It's just that once we get to t equals 3, it needs to go back down to a 0. So what we could do is we could subtract off t squared. Okay, I actually have a typo up above. Let me fix that real quick. T greater than or equal to 3 up there. All right. So in other words, here we have t squared added in. Now we're going to take it away, but only for t greater than or equal to 3. So how we do that? So I can define another function. I'll call it f2 of t, and that is equal to step function of t minus 3 times t squared. And I'm going to put a, well, actually, I'll leave it like that. So that is equal to, if you want to think of it in a piecewise manner, that is equal to 0 for t less than 3, and then t squared for t greater than or equal to 3. So, so the thing is, if I add, or not add, if I subtract these functions, then for t less than 3, I'm actually not subtracting anything. I'm not changing this at all, which is good. I actually want this for all t up until 3. Now, once t reaches 3, and from that point on, I want to go back down to 0. So, but this is equal to t squared. So I'll subtract this, and these two will cancel, but only for t greater than or equal to 3. So f of t is equal to f1 of t minus f2 of t. So now to take a Laplace transform, I can just say the Laplace transform of f of t is equal to Laplace transform of f1 minus Laplace transform of f2, because the Laplace transform is a linear relation. Now, if I write this in terms of the step functions that I'm using, then I'd have for f1, that's unit step function t minus 1 times t squared minus unit step function t minus 3, also times t squared. Okay. So what you could do in general, and I'll have another example after this one, you can express a piecewise defined function as a sum of step functions. So you have step functions times other functions. In this case, adding the step function times some other function like t squared turns it on. Subtracting turns it off. So what's happening here is at t equals 1, I'm switching on t squared. And then at t equals 3, I'm switching off t squared to go back down to 0. So it's a good way to think about it in terms of you want certain functions to be turned on or turned off. And you add them to turn them on, subtract them to turn them off. Multiplied by the right step function to switch them on or off at the appropriate time. So Here I want to switch something on at t equals 1. Here I want to switch something off at t equals 3. Now, so now I can take a Laplace transform of my original function by subtracting Laplace transforms of these two. The problem is I'm not quite ready to do that just yet because they're not quite in the right form. If I look at the rule that I have Laplace transform of u of t minus c, which I do have, and then I have a function of t minus c, which I don't have. All I have is t squared. I need to express t squared as a function of t minus 1 and also t minus 3. So to rewrite t squared as t minus c squared, I'm leaving it as t minus c because I have to do it twice, for c equals 1 and c equals 3. So I'll work out the formula in general, and then I can use it in both cases. So t squared, what do you do? And I did something similar in last class. I can subtract and add the c. So t minus c plus c squared. So you make that substitution, and then you group t minus c together, and you want to keep it together for the rest of the process. Now I can multiply this out, but you must keep this t minus c together. Think of it as a single entity. So that'd be t minus c squared plus 2c times t minus c plus c squared. Okay. So that's the idea. Subtract and add, and then simplify as needed, but keep that t minus c in as one piece. So now I have t minus 1 squared is equal to, t squared is equal to t minus 1 squared plus 2 times t minus 1 plus 1. And similarly, t squared is equal to t minus 3 squared plus 6 times t minus 3 plus 3 squared, which is 9. All right. So I can use this formula up here and this formula over here. Okay. Now, okay, so Laplace transform, I'll need to do this as a multi-line equation. Laplace transform of f of t. So that's equal to Laplace transform of this unit step function times t squared, but expressed in this form. So t minus 1 squared plus 2 t minus 1 plus 1. Okay, minus, and then this term rewritten, and that'll give me u of t minus 3. And I have t minus 3 squared plus 6, t minus 3 plus 9. Okay, so I've just replaced t squared here and here with these shifted forms. Now, the transform of a sum is the sum of the transforms. So what I would do is I would take the transform of this function. Now, when I watch carefully, I go back to a general rule. I need a transform of the unshifted version, the transform of whatever f of t is. And then I multiply that by e to the minus cs, where c is the shift that's being used. Okay. So I'll make a note here. So the transforms I'll need sorry, it's being stupid again. The Laplace transform of 1 is 1 over s. Laplace transform of t is equal to 1 over s squared. And finally, Laplace transform of t squared is equal to 2 over s cubed. Remember, it's whatever power here, it's that factorial divided by s to that power plus 1. So since I have a constant, a linear function, a quadratic function, those are the three transforms that I will need. So for the first part, because it's u of t minus 1, I'm going to have e to the minus s times transform of t squared, which is 2 over s cubed, plus 2 times the transform of t, which is 1 over s squared, plus the transform of 1, which is 1 over s. All right, so that takes care of that part. And then I have minus e to the minus 3s, because I now have u t minus 3 here, and then the transforms of what's in the square brackets here, but without dealing with a shift. So I've transformed t squared, so that's going to be 2 over s cubed, plus 6 times the transform of not t minus 3, but t. You take the shift out, so it's going to be 1 over s squared, plus 9 times the transform of 1, which is 1 over s. And we're done. So to recap, I will do another example coming up, but what you do is first write your piecewise function in terms of step functions times other functions, the functions that you're turning on or turning off. Here we have 3 pieces. That means we're going to need 2 terms like this to get the job done. So however many jumps you have, that's how many terms you need when rewriting as a step function. Then you can take a Laplace transform of each of those terms individually, but you must rewrite each one. Whatever's multiplying the step function here, you got to write it in terms of t minus c, where c is a place where a function is being turned on or off. So once you rewrite in terms of a shift using a lot of algebraic manipulations, this subtract and add trick here, then you can take a Laplace transform finally of each part, and so you use whatever transforms of known functions that you need, and keep in mind, although it's written in a shifted form here, when you take a transform, you transform the unshifted form of it. The shift is taken into account here, the exponential factor out front. Okay. All right, so now I will step through another example to illustrate this process one more time. Okay, so a function we will transform. All right. So the first piece, it'll be equal to t, and that'll be for t from 0 to 2. Second piece, it'll be equal to 1 for t between 2 and 3. And then finally, it'll be t minus 3 squared, no, cubed, for t greater than or equal to 3. All right, so we need to write this in terms of step functions. So f of t is equal to, so what you do is, first, you're turning on t. Now, when you're turning on a t equals 0, you don't need to multiply by a step function, because a step function just u of t by itself is equal to 1 for all t greater or equal to 0, which is the only t that matters for the Laplace transform. So here we can just fill in t. So t is turned on at t equals 0. Next, we're turning something off, turning t off at t equals 2, turning 1 on at also at t equals 2. So what I will do is I'll put in a function that I'm turning on, which is 1, and subtracting a function I'm turning off, which is t. So add to turn on, subtract to turn off. And then here, as I go from t less than 3 to t greater than or equal to 3, I need to do this one more time. I will turn on t minus 3 cubed, turn off t equals 1. So it gets subtracted off there. So that's all it is. Think of what function is being turned on or off, and then at whatever time that turning on or off is happening, fill in the appropriate unit step function. The time at which it's being turned on or off is the shift. Add to turn on, subtract to turn off. So here 1 is being turned on here, so it's being added. Here it's being turned off, so it's being subtracted. Okay. Now we need to get this in shifted form to be able to do a Laplace transform. Anything as a step function in it. So here we need to write this as a function of t minus 2. So what I'll do is 1 minus, and then t will be written as t minus 2 plus 2. And then this part, I don't have to do anything to. It's already written as a function of t minus 3. So now I just need to simplify this part. I have to keep the t minus 2 together. So I'm going to put parentheses around that as a reminder. I suggest you do the same. That I'm not going to touch this. So then I have 1 minus 2. So it's written as minus 1 minus t minus 2. All right, and then I have the other term. Okay, so this is what I'm going to actually take a Laplace transform of. So Laplace transform of f of t is equal to, first is just, so focus on this. This is what I'm taking a transform of. So I can handle the terms individually. So I'll have Laplace transform of t plus transform of the part that has a unit step function at t equals 2 plus a part of u of t minus 3. Okay. Now, transform of t, we saw that earlier. That's just going to be 1 over s squared. That's all we need to do there. And here, I'm going to, because of a shift, unit step function of t minus 2, that's going to give me an exponential, e to the minus 2s, times the transform of all this, the unshifted form. So I have a minus 1 over s for a Laplace transform of 1, and then minus 1 over s squared, Laplace transform of not t minus 2, but t. Okay. So that takes care of that part. And then finally, for this part, I'm going to have an exponential, e to the minus 3s, and then I have a Laplace transform of t cubed, which is going to be 3 factorial, which is it's 6, but as a factorial, over s to the 4th. Remember, whatever power you have here, that factorial goes up top. The same power, s to the same power plus 1 goes down below. So this would be 6 over s to the 4th. And then minus the Laplace transform of 1, which is 1 over s. Okay. And we're done. So when we see differential equations that have a piecewise defined function on the right side, you take a Laplace transform of both sides of the equation. How we handle the left side is what we covered last time. The right side, you'll carry out this kind of procedure. So you'll write your piecewise defined function in terms of unit step functions, and then whatever's multiplying each step function, get it in the appropriate shifted form using a subtract and add trick. And then you can take a Laplace transform of each part individually using a transform I showed you that you have using this rule right here, which is why you have to get it in shifted form. And after that, this will figure into the Laplace transform of a solution of your differential equation. So what I'll do in the next video lecture is to apply this technique for solving differential equations with these kind of piecewise defined functions on the right side, carrying out this transform procedure, and then showing you how we invert the Laplace transform in that case. And the thing is, since we have these exponentials here that come from transforming step functions, that indicates that the solutions of these differential equations will also be expressed in terms of these same kind of unit step functions. So that's something that you'll see next time.